What we're going to learn about today is how we can find the stationary points of a function that we're given, as well as to be able to classify the nature of the stationary points. Now, stationary are points where the slope of a function is equal to 0. So if we consider we've got an unknown function f of x, we know that its stationary points for f of x are going to occur when f dash of x is equal to 0. Does that follow? Because that's when it's going to have a slope of 0. Now, if we have a look at this funky little graph below, this should line up similar to the handout that I gave you. When we look at this, have a think. We ask ourselves, when is this graph going to have a slope of 0? Well, the first one that we see is it's over here. Because if we drew a tangent, it would be completely horizontal. So this part over here, this is a stationary point. It's got a specific name, but I'll put it down later. The next one, when the graph is going to have a slope of 0, is down here. And then there's a final one. It goes up, then it gets a slope of 0 here. It's quite exaggerated on the board, but you can see it's got a slope of 0, and then it starts going up again. Now, the cool thing is when we combine these with a sign diagram below, hopefully this is straight. Yep, close enough.
Yeah.
We're able to start classifying the behaviors. So down here, this is going to be our sign diagram for f dash of x. Without even having to know what f of x is, we can do a sign diagram for f of x because we think, what does f dash of x tell us? It tells us the slope of f of x. Now, Levi, I'm going to ask you a question. Over here on the graph, the very far left, as you read the graph from left to right, the values of x increase. What is happening as the values of x increase? What is happening to the values of y?
From left to right.
From you're reading the graph from left to right,
It increases.
it is increasing. And because of that, if it's increasing, it's going to have either a positive or a negative slope. Which one? Positive. So what we would say is that the slope of this graph f of x, the slope of the graph f of x is positive, so therefore f dash of x is going to give us positive values. Emma, I'm going to pick on you. Here to here, as you read the graph from left to right, the values of x are increasing. What is happening to the values of y?
They're decreasing.
They're decreasing, which tells us what sort of values of f dash of x are we expecting?
Negative.
Negative. Next, Foreman. As you read the graph from left to right, the values of x are increasing. What is happening for the values of y as you go from here to here?
Increasing.
Increasing, so what sort of f dash of x are we getting?
Positive.
And then finally, Alyssa. As you read the graph from left to right, the values of x increase. What sort of slope are we expecting from here onward? Positive. And this is the sign diagram that helps us understand what's happening with the graph. As you go from an increasing slope to a decreasing slope, what you end up finding is a stationary point. And we call this one a local minima. Or minimum. It's up to you.
Can they also be called turning points?
Yes, you would call them a turning point as well. All turning points is actually, it's a turning point, yes.
Is that a minimum? Or
Minima or minimum, you can call
would that
it.
be a maximum?
Yes. It's been a long day. It's a local maxima because it's got a maximum value. Okay, the next one. Where would we see our next local something or other? At a turning point or stationary point?
Down
Booyah. This guy over here. this is a stationary point, also known as a turning point. And it is called a local minima. Now there's one more here. There's one more stationary point. It is occurring when the graph goes from increasing to increasing. This guy's a special guy. It's a stationary point. Point of inflection. You can spell it the old English way of using an X, or the English way of using an X, or you can use the modern English word where it's CT, point of inflection. Now when we look at this, think about when you expect to see maxima, minima, and inflections. When would you expect, looking at the sign diagram, when would you expect to see a local maxima? Yeah, when you're seeing a positive slope transforming into a negative slope. That's when you're going to see a local maxima. What about a local minima? Where would you expect to see that?
Negative turning to a positive.
Yeah, negative slope turning into a positive slope. So it's gone down and now it's gone up. What about if there's a stationary point, but it was going negative to negative or positive to positive? What sort of point is that? Point of inflection. Now, here's the next question. Where might we expect to see the minimum or the maximum values? We would expect to see the minimum or the maximum values either at the maxima and minima or at the extremes of the domain that we're graphing our graph over. Does that make sense? They can occur, maxima could occur here. Well, basically, we wouldn't know whether they're maxima or minima. So that means a maximum or a minimum could occur here, 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 or here. It all depends on how big your domain is, if you even have a constricted domain, and how the function is just behaving in general. Seem okay? All right, so that's the, I guess, qualitative idea behind everything. Now let's have a look at the quantitative practice, or the math. Consider we have y equals x cubed minus 6x squared plus 5, and we are considering this over a domain of x can be between minus 2 and 5 inclusive of minus 2 and 5. We want to find the greatest and the least values. Now we could put this in our calculator and we could just figure it out by either graphing or by sticking in values. But is there a way that we can find the turning points or the stationary points?
Probably. Yeah, probably.
Mr. Jaff, what could we do to find the stationary points?
Find the station. Is there a rule for it?
Is there some sort of rule we could use to find stationary points? We could maybe find the derivative and set it equal to 0. So if we get dy over dx, we discover that that's going to be 3x squared minus 12x, and we say by constant, and then set the left-hand side to 0. And what we end up searching for are the zeros of the expression on the right, which will reveal to us the values of x at where the stationary points occur. Because this is a quadratic, we have to use the null factor law. So divide by 3x. And that's going to be x take 4. We can get rid of the 3 there because just divide everything by 3. So therefore x is going to be 0 or positive 4. So does that make sense so far, guys? I might just... What happened to the 3?
Oh, no, I get it. No, one of the x's turned to
Yeah, you just divide both sides of the equation by 3.
Yeah.
Is that okay so far? All right, now, what we could do from here is using this sort of knowledge, we could actually graph this, or we could graph that function without using our calculators. We're not doing it this lesson, this example. You're doing it this lesson, but not this example. Instead, what you could do is you could just do a sign diagram, and it allows you to reveal the locations of your minima and maxima, because we know when we go from a positive slope to a negative slope, there's going to be a local maxima. When we go from a negative slope to a positive slope, we're getting a local minima. And then we could see either a maximum or a minimum, or maxima or minima at the extremities. So, suppose we want to figure it out. I'll start off with a sign diagram. This is going to be -2. This is going to be 5. I then have to put these guys on here. I'll just say 0 is over here, and I'll say 4 is up here. Everything else I don't care about. Now the question is, what is the behavior of the function? F dash of x at these intervals here. Any ideas? What could we do to figure this out? We know that there's going to be stationary points here and here, so it's going to be 0. But the question is, what is the slope doing here, here, and here? So at this point, we just take random values between these intervals to figure out what the slope is doing. So we could start off and say f prime of, what's between -2 and 0? -1 is going to be 3, -1, all squared, -12, -1. Now the question is this going to be larger than 0 or smaller than 0? Three take -12, greater than 0, so therefore you're going to get a positive gradient. What's that one? Let's see back there, please. So there's our first part. Next part, what's the value between 0 and 4? 2. Okay, 3 times 2 squared, that's going to be 12. Take 24, that's going to be less than 0. So what should this guy be here? Positive or negative? Negative, because it's less than 0. Next one, what's the behavior here? Is this going to be a point of inflection, or is it going to be a stationary, or sorry, a turning point? Think about the order of the function up here. Up here.
Point of inflection. No, yeah, it's a turning point.
Is it?
Is it? Oh no, now I'm confused.
How many times do you cut the x-axis?
Oh no,
Okay, f of 4.5 equals 3. 4.5 all squared, take 12 times 4.5. This is going to be about 48-ish, a little bit more. This is going to be 16 times 3. So what's that? Does anyone want to calculate that?
Sorry, what was the?
The first is 60.75.
60.75 here, or 60.75 take.
Take.
It's going to be positive.
Oh, wait. I forgot the negative. Negative. 54.
This is negative 54, so it will be positive, because this was 60 something, this was
Yeah.
50 something. So, it goes positive. All right, now let's look at this. Question?
So isn't that because like your first original equation up the top, that's a positive, that's a negative, that's a positive? Is
Positive, negative, positive.
That, is that why that's positive, negative, positive?
No, I'd say it's just coincidence. But if we had a few more, we could put a conjecture forward. All right, have a look. This is our sign diagram. Question is, transitioning from here to here, what will this stationary point be? A local minima or local maxima?
Wait.
At
That's
0, local minima or local maxima?
maximum.
Why?
Because it goes up and then down.
And then it goes down.
Okay. At x equals 4, what are we going to expect? Minima or maxima? Okay, now next part. Extremities of the function. What could potentially be here? I say potential because we haven't checked yet. Potential? Potential maxima or potential minima?
Wait.
Here,
Minimum.
-2. Why minima?
Because in order for it to be positive, it needs to be coming from the negative.
Yeah. It's a potential minima because it's increasing and it's going to hit a local maxima here. So if this was the max, if this is the minima, then it's going to reach the maxima. If this, we thought it could have been a maxima, it would always be smaller than this guy. All right, Harrison, what do we expect at 5? What could it potentially be?
Local maximum.
Potential local maxima, why? Think about it. You are at the lowest point possible here,
Yeah.
because this potentially is the minima. I mean, that could potentially be a minima, but you're low and then you're increasing. So by the time you hit 5, you could have potentially be at the maxima for this interval. Does that make sense, guys?
Yeah.
Okay, now the question is asking, find the greatest and least value. How might we find the greatest? Any ideas?
Isn't that just a local maximum?
The greatest value is going to occur at the potential maxima and the local maxima. So what should we do to find out which one's bigger?
Substitute both into our initial equation.
Indeed. Top didn't start. Okay, so finding maxima. This is where I'm going to need you guys to help me out. We're going to pick f of In this case, 0. That's going to be 0 cubed minus 6, 0 squared plus 5. That's just 5. Next, we have f of potential maxima, or not local, potential maxima is here. That's at 5. 5 cubed minus 6, 5 squared plus 5. So that's 125. Take 25 times 6 plus 5. What would that be?
5 times.
Oh, I didn't get you calculators. Sorry.
Negative 20.
Negative 20. Oh boy,
Take
that didn't get very big at all. Okay, so therefore maxima are at
5 or 0.
what is more?
Okay, maximum value of 5 at x equals 0. Finding the minima. What values should we test for? Harrison, focus. What values should we test for to find the minima? Where's the potential lowest value?
The potential
Yeah.
mirror and local mirror.
Okay, so we need to calculate this one, and then we need to calculate that one there, f of 4. Sixteen fours are 64. Take 24 plus 5. It's 45. I don't think that's right. I don't think that's right at all. Oh, it's 16 times 6.
First one's
Negative.
negative 27.
Negative.
And then this one.
Negative 27.
Lowest value at. Comprende? Do we understand how calculus can be used to find these values? Is there a quicker way to do this?
Hopefully.
You'd probably, if you just had to find them, you would probably just find the stationary points and then go straight to there. But doing this way, it's an analytical way of building up to that. This shows that you understand how calculus can be used and the power of it. Seem okay? All right, in a few days' time when you get your investigation, you're going to be designing the optimal size of a cake tin to cater for volume. You're going to use this sort of math to be able to pick the correct scaling of your cake tin to maximize the volume. So there is an application to this. I promise it's actually not that hard. It just looks tricky because it's the first time you're seeing this. Any questions? All right, I'll grab the calculators and we'll do a little bit of calculator work in about 20 minutes.